So thank you everybody for coming to a Pawsey talk on the past, present, and future of quantum computing from one of the experts in quantum computing, Jonathan Wurtz. Welcome to everybody online and in person. Just to let everybody know, we're going to be recording this session. And also we have people who are online to monitor online questions. So if there are questions online, there'll be people to forward it. And for in person, we've got a mic. And before we start the talk, I'd like to acknowledge country. So in the language of the Noongar Whadjuk people, Nagala Kadich Noongar Mut Kayen Kadich Nija Bujo, I acknowledge the traditional owners on this land, the Noongar Whadjuk people, and their ancestors and elders past and present, as the traditional and original custodians of this land, where Pawsey sits. And I'd like to pay my respect to any traditional, the custodians of traditional, the traditional owners of the land on which people might be joining, and pay my respects to also First Nations people everywhere. Now, before I dive into Jonathan's expertise, I will mention that this is going to be a very cool talk on the high-level view of quantum computing, a bird's eye view of its current status and where we're going. And it's going to be presented to you by Jonathan Wurtz, who is a quantum solutions lead at QueRa Computing, one of the leads in neutral atom technology. And he's been working over 3 years to kind of get this neutral atom technology off the ground and have algorithms built for this type of technology. He leads the theory group to leverage these neutral atom technologies to solve hard computational problems. Jonathan got his PhD in Boston University in 2020, studying theoretical quantum non-equilibrium phenomena in condensed matter systems. And he's really excited to push these fields and other aspects that might be solved by quantum computing across the entire sort of software stack as well, from compilers to hybrid HPC integration, algorithm development, and application code design, which actually we work quite heavily with Jonathan on those various aspects as well. I'll let him introduce you to neutral atom technologies, but also the broader view of quantum computing. Thank you, Jonathan.
Great. Thank you, Pascal. Good. So I guess today I'm looking forward to sharing, I guess, as Pascal described, kind of broad view of quantum computing. I guess I like doing this sort of as a colloquium style where it kind of jumps in and out of technicality, depending on if you're interested to learn more. I guess there should be at least enough keywords to dive deep. I guess if anyone's interested in talking afterwards, I'm happy to do so. I guess I'm looking forward to, I guess I'm going to be here till Wednesday. So if anyone's here, feel free to chat. Good. So maybe I can kind of start off at a high level, reflecting on an allegory of sort of the invention of the microscope. I guess in the late 1600s, Antoine von Leeuwenhoek looked through the microscope. I guess he invented a new microscope with more magnification, and he saw basically lots of little single-celled organisms, swimming around in his view, and basically this kicked off the field of microscopy and microbiology. And in the same way, like this was basically enabled by the invention of the microscope. And I guess if I can do this by allegory, possibly quantum computing can be a similar scientific tool to the microscope in that it can let us explore different things and explore fields we might not even be conceiving of today. I guess that's maybe a philosophy slide, but I guess that at least gives us some ambition for the future of quantum computing for science. Maybe with that, I can take a step back and talk a little bit more about, I guess, what I'll talk about today, which is roughly in 4 parts. First, I'll talk a little bit more about QueRa Computing, which is my company. Next, I'll talk about, I guess, why quantum, so the algorithms and applications that run on, which have promised to run on quantum computers. I'll talk about some of the different hardware modalities, as well as the algorithmic and software modalities that actually let us run algorithms. And then I'll finally touch on this notion of quantum co-design, which is actually trying to make best use out of today's and tomorrow's near-term computers. Good. So maybe I can start with an introduction. So this is just our corporate slide on QueRa Computing. So we are a Boston-based startup that builds neutral atom quantum computers. We've been around since 2019, either 2019 or 2017, depending on sort of incorporation date. And we build neutral atom quantum computers and are the scientific leader in neutral atoms. We're really looking for quantum utility with these things, which means that we're really becoming the forefront in things like quantum error correction, as well as very promising in terms of scaling these devices. Our first offering is called QuEra, which is our first generation computer, which has been accessible to anyone for over 2 years on Amazon Bracket. Basically, you're able to program, and I'll say this a little more later, in this special analog mode, which is great for science and scientific exploration. What's cool is basically you're able to do scientific research from your laptop because it's a cloud-based device. So we have this SDK, which we call Blockade. You're basically able to program a wide range of R&D and science applications to then run on QuEra, and then you can collect your results and analyze your results and so on and so forth. So this has been available for over 2 years now, or like 2.5 years now on the cloud. We have a proven track record of basically very high uptime for this device. And next up is we're building a gate-based computer. So this is a picture of our Gemini class machine in our lab. And this is a gate-based device with order 200 physical qubits. And this is actually going to be at the ICE the ABCIQ supercomputer at ICE, where it will be sort of built and integrated and be part of sort of the next generation quantum supercomputer. So this is our next step, but of course we're looking at a much longer roadmap than that. And I'll briefly flash our slide on our roadmap. So I guess we say that in 2023 we'll have QuEra, which we did. In 2024 we'll have this first generation, or I guess second generation device, which is Gemini, which will have demonstrations of up to 10 logical qubits, which we actually achieved in December of 2024. And then as we move forwards, we have our third and fourth generation, which will have more and more qubits. Our next generation machine with say 3,000 physical qubits and then over 10,000 physical qubits, which is one of the unique advantages of neutral atom computers. Great. So maybe that's enough about QuEra. I guess this is a general talk, so I should try to stay general. And I guess maybe one big question to ask is, like, what is quantum computing? And in some ways, this is a very hard slide to make because this is a very sort of broad and complex field. But what makes quantum computing so special? And what makes quantum computing special is this notion of qubits, which are a different mode of representing and processing information, which can, basically instead of a binary 1 or 0, is some different object. And this different object gives us, I guess, 3 fundamental properties of superposition, entanglement, and interference. And we can use these 3 properties to basically execute computations by basically modifying the state of these qubits and then doing measurements which, for example, through interference, enhance the solutions that we're looking for our computation. In fact, there's also the variant, I guess, usually when we think about quantum computing, we think about superposition like this dead and alive cat. But in fact, it's really this entanglement and interference patterns, which is really what makes quantum computing powerful. And in fact, this new modality means that you can actually get different kinds of algorithms than you might expect versus classical hardware, which we call quantum speedups. Typically, these are speedups with caveats, right? Which means that typically it's for, say, very structured instances, or you require other abstractions such as quantum memory and other things. But nonetheless, there's algorithm like Grover search, where you can find some marked item in a list instead of in order n time, which is the random search. You can actually find it in order square root n time, which is basically due to this quantum interference phenomena. There's also, say, things like the HHL algorithm, which is used for matrix multiplication, things like quantum Fourier transforms and hidden subgroup, as well as things like quantum walks, which is, I guess, has a strict algorithmic speedup. So like all of these sorts of algorithms tell us like that there do exist on perfect hardware the ability to do things that are very hard to do on existing classical hardware, but they require basically this next generation of hardware to actually be able to execute these computations. And if I can sort of bring it back, I guess, with another allegory, I'm actually going to have a slightly offbeat allegory here, which I learned about recently, which is thinking about actually the advantages that we get out of new forms of computation and what we might, what might quantum computing look like in the future. And actually, I'm going to be very offbeat. I'm going to say civil engineering. This is actually a fun thing that I learned. In the 20th century, large bridges were typically suspension bridges, right? Which are basically just have a wire which goes across, and these are relatively expensive to build, but very simple to simulate. And in fact, modern bridges, like almost every bridge large bridge we see today, are these cable stayed bridges, which are much cheaper to manufacture, but require much more intense computational tools to actually understand the stresses and strains on these bridges so that they can actually be built safely. And in this way, these modern computational tools, in this case, engineering and civil engineering design, enable this more efficient bridge design. And one might imagine maybe, if I'm talking about the future of quantum computing, maybe 20 years from now, we might have a similar thing where it's just natural for us to have, individualized drug design where we use a quantum computer as part of our workflow. And really, we, in the same way that we drive over these bridges every day, we might have this in the background of everyday life. Good. So with that, I guess I can bring us to the promise of quantum computing and some of the algorithms and applications we might have. There's sort of three main applications of quantum computing, and the spooky fourth, which is code breaking. So these are optimization, which is trying to solve hard combinatorial problems. There's machine learning, which is to say trying to do inference or learn from data. Then there's simulation, which is, as it suggests, basically trying to simulate quantum systems using a quantum simulation, a quantum computer. And finally, code breaking, which is based off of Shor's algorithm, which is to say that you're able to factor large composite numbers into their primes exponentially faster. So if we just go down the track of the different of these different applications, first is quantum optimization. So this is typically combinatorial optimization, which is you basically want to find some solution in a very large domain of solutions which maximizes some objective. These are ubiquitous. They're seen everywhere. Things like, traveling salesman and other NP problems, say maximum independent set or scheduling problems. But then we can also have other descriptions which are also relevant, such as satisfiability, right? Which is you want to find a maximum number of binary variables that satisfy some clauses. And then things like integer programming, where you want to maximize some objective given, say, your domain is integers, which makes the problem hard. So this is like sort of a broad class of these problems, and typically we can take some real world mess and sort of smush it into one of these forms, solve it in that form, and then hopefully your buses get routed 10% faster than they would otherwise. Now there are several algorithms which have been used for quantum optimization. Typically, these have some sort of heuristic advantage. It's pretty hard to see explicit advantage for these, especially given the dominance of classical methods for optimization. One is, of course, Grover search, which is what I described before, which finds a quadratic speedup for unstructured search. There's also heuristic algorithms like the quantum approximate optimization algorithm, QAOA, which is a heuristic advantage in time and solution quality. And actually, I'd also like to shout out a recent idea from Google on something called decoded quantum interferometry, which is using fault-tolerant devices to basically do amplification or polynomial enhancement or amplification of good problem solutions for very structured problems. So I guess these are now some of the algorithms that we might use for this optimization. Now, of course, these excuse me. Of course, this is quantum computing, so we actually want to show that this is working. So we've actually run this on real hardware. So if I can sort of shout out some of the major recent results, there is, of course, this, I guess, flagship results by Google in 2021 of QAOA, which actually shows some improvement in low depth algorithms. Then there's some great work out of our friends at Harvard and QuEra in 2022 on quantum optimization on neutral atoms. And then actually a third one is some great work out of JP Morgan and Quantinuum in 2024 on solving hard problem instances. I guess there's many more, but these are at least the standout ones for me. I think actually this quantum optimization of max independent set stands out in particular for being the largest problem instances that have been solved on a quantum computer with up to, I think, 200 or so qubits, or 200 or so variables. Good. So with that, there's quantum simulation, which is sort of the second application. And this comes out of a vision from the scientist Richard Feynman, which is, if we have quantum computers, why don't we simulate quantum systems using these quantum computers? Which is to say, we try and map the exponential complexity of some quantum system to the exponential complexity of a quantum computer. And this is actually where a lot of near-term quantum applications comes from. And actually, this is where our QuEra device really shines, because it was really meant for simulation. But we can think about things like computational drug design. So say I have some molecules and I want to fit them inside of a protein. Things like molecular characterization, where I want to understand the structure and function of some large or complex molecule. And of course, things like condensed matter systems, where I might discover interesting new phenomena such as, room temperature superconductivity, which is the so I guess there are many advances of hardware, and there's actually a little tricky to narrow down this list for what we have done already. But one that I'd really like to call out is there's this great paper or series of papers from Harvard / QuEra. It's a little, like, sometimes the author lists are very mixed, on quantum spin liquids. There's some great work on IBM, on Ising models, some work on molecular ground states from Microsoft Quantinuum. There's some very cool work that we did on Aquila on quantum field theory and false vacuum with QuEra and NERSC last year. There's this recent results, which I think everyone loves to hate, on D-Wave, not D-Quave, D-Wave, in last year / this year. And of course, some molecular simulation work from IBM, which is also an interesting work in that it also considers the framework of both classical and quantum computing in the same. Of course, I would really like to shout out some of the recent work that also Harvard QuEra did on using our reconfigurable neutral atom platform for simulating topological matter and fermion dynamics. And I guess this, like, as you can see, like, as we grow out, right, from say 2021 to 2024, we're really using these computers at scale. We're leveraging tens or hundreds of qubits to actually implement large and non-trivial phenomena to really understand what's going on. Good. So that survey is a bit more on quantum simulation. Next is machine learning, which is, I guess, everyone likes to say quantum AI. I don't know what quantum AI actually means. I just see AI as inference and sampling. And by golly, our quantum computer is great at sampling from non-trivial probability distributions. So in this way, things like generative quantum machine learning, I think, is one of the next steps in thinking about basically using a quantum device as part of a larger workflow for machine learning in general. So this is like, say, using your quantum computer as a kernel for like an autoencoder, for example, or using it as say a kernel for classification tasks, for example. The challenge, of course, is that for most of these algorithms, they are heuristic only, because typically we're focused on sort of NISQ era of computing so that we can actually execute it on hardware. And there are only sort of suggestions of increased expressivity and memory advantage, and maybe a few more. This is sort of where I like to challenge the field to think about not necessarily just taking classical models and putting quantum hats on them, but really considering new ways of executing computation. Now, in the same way that I did recent advances in simulation and optimization, I'd like to share some recent advances in quantum machine learning. Though actually, it ends up being a little bit awkward because it's pretty challenging to actually do non-trivial things with machine learning at scale. So I'm actually only going to have two, and I hope I don't sound too biased by having the first one be a flagship paper by IBM in 2019, which uses, I believe, 5 qubits to do some machine learning tasks, and then jump all the way to our recent work on quantum reservoir computing using neutral atoms, which is basically a way of using your non-trivial quantum dynamics as a kernel or a reservoir, sort of a similar thing, in order to do classification, regression, and possibly generative machine learning tasks. There is a lot more for theory that's been done. And like, especially as we get more and more powerful computers, we can sort of suggest and think about more ways to move forwards. But typically, a lot of these experiments are done using simulation on, say, 20 or so qubits, and don't actually need hardware. So in this way, actually, like, it's not like really real machine learning unless you're using 100 qubits. And I believe this reservoir computing work used order 100 qubits in order to actually do what it does. So this is a little funny because it's only really one, which is us, but I think that does suggest QuEra as one of the leaders. Great. So I think with that for advances in quantum machine learning, I'd like to jump to the last spooky one, which is quantum code breaking and encryption. And now this is basically we have some very powerful subroutines of quantum phase estimation and the quantum Fourier transform to solve something called the hidden subgroup problem, which is a group theory problem, which ends up mapping very nicely onto number theory. And Shor in the 90s, I think, figured out that they could use this to factor large composite numbers much faster than into prime factors much faster than any existing classical algorithm. What this means, of course, is that RSA, which is basically the way that we encrypt most data on the internet, is founded on the hardness of prime factorization, and therefore can possibly be beaten by quantum computers. But I guess don't worry, it requires thousands of logical qubits and T-gates, which won't happen for a while. Asterisk. It's always a funny question when someone asks me like how long, because it's like a national security thing, I guess. So I won't say more on that. Now, with the survey of those four main areas, it's natural to ask, are there more applications, right? Are we missing, missing sort of the killer apps or the key things we're doing with these devices that really just having them, right, will actually enable us to do discovery. And I'd actually like to add another allegory here of thinking about telecommunications networks in the early 2000s. So I guess in the late 90s and early 2000s, right, billions of dollars were spent on building out 3G telecom networks, right? Billions and billions, people, reserved all sorts of bandwidth for these things. But the challenge is that no one really knew what they were going to be used for until 2007, I guess, was the first smartphone. And then basically Apple was like, great, we can use all this bandwidth to actually, basically get these things to use the 3G network in a way which no one had really thought about before. And in this way, basically by building out these telecom networks, they enabled basically, our modern sort of cell phone or smartphone-based, culture today. Of course, the allegory is that for quantum computing, we're also thinking about the same thing, right? We're spending millions and billions of dollars on building out these devices, and we know some hints of what's coming, but there's also this question, of what are problems that are so hard that we're not even thinking about them, right? I think that's really a thing to consider, right? Of not just, oh, this is a hard problem that we're trying to solve today, but what's it like what's a problem that we're not, that would be great if we could solve, right? But it's only enabled by this new computational modality. So I guess I leave that as a bit of a challenge, especially for everyone here who is very supercomputing focused, where you have a beautiful tool and want to use it. So with that, I'd like to shift a little bit and talk a bit about the different modalities of quantum computing. So I guess there are 4 major modalities. There's adiabatic computing, which is typically used to find ground states of combinatorial problems. Analog computing, which is what QuEra uses to do science. Digital computing, or gate-based computing, which is a universal mode of computation that lets you basically do any computation with the challenge that I guess noise and decoherence limits the power of the devices. And there's logical or error-corrected quantum computing, which basically, through very particular structure of your quantum executions, lets you remove errors from your computation in order to do very deep and powerful algorithms. So if I can just go through, I guess adiabatic quantum computing was sort of the first. I guess if you think adiabatic or annealing, you think about D-Wave, which is one of the first quantum computing companies. In this sense, you're specialized to optimization problems where you encode the solution to some optimization problem to the ground state of an Ising model, use some transverse term to anneal from some easy to prepare state into some hard to prepare state, which encodes your solution. And if you do this slowly enough through sort of this quantum phenomena, you actually follow the ground state at all times, or you follow a low energy state at all times, which is called annealing or adiabatic evolution, in order to prepare this target state. And this is something which D-Wave has been doing for years and years. They have some nice results. The challenge, of course, is that this mode of computing is fairly limited to combinatorial optimization problems, because you need to basically encode it into the ground state of basically an Ising model. So I guess that's all I have to say about adiabatic quantum computing, because I guess the next step up is something called analog quantum computing, which is now you have fully coherent, time-dependent Hamiltonian dynamics, right? So I guess if anyone's familiar with this gate-based model of quantum computing, we also can draw the gate-based circuit, which is basically you start with some zero state, and they just do Schrodinger's equation with some Hamiltonian, right? And in this sense, right, this is actually the Hamiltonian which we can program on QuEra, our device, where basically you program, say your Rabi frequency, phase, the tuning, and positions of each of the atoms, and then execute these non-trivial dynamics in order to do interesting scientific discovery. And I think this is important. It is powerful but non-universal. So this is sort of where this notion of co-design comes in, where we need to make sure that we are understanding the problem, we're understanding the hardware, and we're able to map between the two in order to get the best use out of our device. Now, QuEra is analog. So this is, I guess I showed QuEra's Hamiltonian. So this is the device we have at QuEra, and has been used in this mode for scientific discovery for over 2 years. Great. Next up is digital mode, or NISQ, which stands for Noisy Intermediate Scale Quantum, where we implement a universal quantum programs by a sequence of gates acting on qubits. And what this does is this modifies the state of the qubits in a non-trivial way, so you get your entanglement and interference, in order to amplify or do some other task through some measurement on the outside. Of course, the challenge is that in these near-term devices, because this is still sort of an analog mode, right, where basically you just have some sort of your qubits are sort of interacting with the environment, your noise and decoherence still limit the number of gates before the signal is lost, which means that you're still sort of limited in the power of these devices. Though, of course, you can program in a wide array of SDKs and hardware. I guess Qiskit, Circ, and now Blockade, actually now, which is QuEra's SDK. Blockade now also has a mode for programming programming circuits as well. This is digital mode, and now Gemini is digital. It's actually sort of a funny thing where Aquila is analog with an A, Gemini is gates with a G, and I guess we'll have something with an L for logical. I don't know, we'll see. But our next generation of device, which we're bringing over to ICE, and has lots of and has some demonstrations already, is working in this gate-based or digital mode, and we have some strong demonstrations on that. Great, which of course brings me to recent advances in gate-based computing. If I talk about the past and present, none of that is, of course, I can't start without talking about Google's presentation in, I guess, 2022 on quantum supremacy, which is basically a sampling experiment to show that basically it's very hard to simulate the action of a quantum computer. More recently, I guess this is 2022, then 2023, there's a paper by IBM on, I think, simulating Ising models in a way that you can mitigate noise and errors. In 2024, there's this great paper by, again, I already called out for optimization, by JP Morgan and Quantinuum in 2024, solving a hard optimization problem. And of course, there's this excellent paper by our excellent work by our friends at Harvard and QuEra on probing topological matter and fermion dynamics, which is this simulation problem on hundreds of qubits using our reconfigurable architecture. Of course, the challenge with gate-based mode is, as I said, the notion of noise and decoherence. So here, your physical qubits suffer from basically, if you have some state, that state may be affected by the local environment. So what we can do instead is try and encode a logical qubit within many physical qubits, so that when I actually have effects from the environment, it may change the state of the physical qubits, but the encoded qubit within those many physical qubits hopefully doesn't change. The classical analog here is, of course, error correcting codes, right? So this would be, say, the repetition code, which is to say, I take a binary 0 and I encode it into many different zeros, right? Say, in this case, 6 zeros. And then I take a 1 and I turn it into 6 ones, right? And now what happens is I encode that 0, right, into this logical 0 into my channel. And then I run it through, say, memory, or I send it over the internet or something like that, and I may get some errors out, right? So maybe some of my bits flipped from 0 to 1, right? But now what I can do is I can figure out what those errors are, right? And then in this case, I just do a majority vote, right, to say, oh, I see 4 zeros and 2 ones, so that must be a 0, right? Or similarly for 1, I send it through that channel. I see 5 ones and 1 0, so that must be a 1. Or maybe I flip 3 errors, and then I don't know if that was a 0 or a 1. And in this way, I have some code distance where I have basically I'm able to encode in several physical bits, robustly able to encode a smaller number of logical bits. So this is what we do for error correcting codes. And I guess the repetition code is sort of the simplest case. There's a vast majority of different codes, I guess, such as like LDPC codes and the like. But the challenge, of course, is for quantum computers, we can't really do the same thing, right? Because there we have this funny roadblock called the no cloning theorem, which is to say you can't duplicate one qubit and copy it into another, right? And this is basically because measuring your qubit, right, like observing your qubit changes the state and removes quantum information. So what we can do instead, and I guess as well as this, right, for the, sorry, I didn't say it here, I probably should have, for the repetition code, right, this fixes bit flip errors, right, so 0 to 1 and 1 to 0. But for the quantum computer, we also have phase information, right, which is to say I'm in the plus state or the minus state, right? So we also need to be able to preserve this phase information as well as this bit flip information. So what we can do instead is we can encode the logical qubit into a subspace of physical qubits, right? And then by encoding this into a subspace, right, we might have many different equivalent quantum states, right, which map to the same logical state. And then what we can do is we can take measurements of ancilla qubits, called syndromes, and basically figure out what errors happen on the quantum device using something called decoding, and then do some operation to push the qubit back into the correct subspace. And this is basically the big magic of error-corrected computing, is even if you have errors, you're still able to encode your quantum information. Now, this error correction step ends up being a pretty hard classical computational challenge. So actually, if we're thinking about the future of quantum computing, there's going to have to be a lot of classical computing involved in that picture as well, doing this syndrome decoding. Now, the canonical quantum code is something called the surface code, which you can sort of see as two repetition codes, not like ish, where basically you have, say, like a Z repetition code in one direction and an X repetition code in another direction. It's actually not quite true because it actually goes this way and this way, but that's why I say it's ish. But basically, you're able to, through these syndrome measurements, determine the X and Z bit flip errors, and then from there you're able to basically support some small number of errors in order to actually do some deep computation. So there's the surface code, which is actually what Google demonstrated, but there's also a vast majority of other codes, such as color codes and quantum LDPC codes, I guess are my two favorites. And I guess one of the cool things about neutral atoms, I think, is while Google and and superconducting chips are sort of forced to be with the topology of their chip, something that reconfigurable atoms can do is actually explore many different error correction codes to figure out which one is particularly best for the particular application. Good. So maybe to emphasize a point, I should just say that this error correction is really what enables like real quantum utility, right? So if we really want to do these large and powerful and deep simulations, or like say we want to simulate some large and complex molecule, or want to break RSA, or we want to do some hard optimization problem, we need very wide circuits, right, which means many qubits. We need very deep circuits, which means lots of accumulated errors. And by using error correction, we are able to remove those errors and therefore actually do all of these powerful algorithms and subroutines. So in this way, by building out error correction, right, this is really what will bring forth the future of quantum computing. And recently, I guess there have been some advances in this logical or error corrected mode. The first to come out in I guess it starts in 2024, which is actually sort of a highlight of how fast this is going. In 2024, Google came out with a paper announcing quantum error correction below the surface code threshold, basically using these surface codes. Actually, the previous slide was from this paper, where they demonstrated basically a single long-lived qubit. There's also some great work out of using neutral atoms from QuEra and Harvard, also in 2024, where now instead of one qubit as just in memory, it's up to 48 logical qubits doing actual small algorithms, some of which are hard. Next, there's some results on Quantinuum on 40 surface codes, basically using a different small color code to do some memory. And then finally, I should also emphasize this notion of experimental demonstration of logical magic state distillation, which I'll touch on a little bit later, which is one of the important primitives for error correction, which is put out by QuEra late last year on the Gemini device. So that's, I guess, all of that happened in 2024, right? And there's a lot more that's going to happen this year. And I think really like this year and the next year is really going to be like the year for lots of very exciting and scaling of logical mode devices. So that's like, if I'm talking future, there's a very big ellipsis here, which suggests lots of interesting things are coming in the future. Now, if I put it all together, I guess there's this notion of quantum supercomputing, which is to say that your utility scale computer is hybrid, right? Which is to say it's not just going to be some QPU, but instead it's going to be actually an orchestration of both the QPU as well as lots of different heterogeneous resources, right? So say you might have GPUs doing decoding, you might have CPUs doing compiling tasks, you might have an FPGA actually generating signals for your device and doing real-time feed forward. You might have, some interfaces that actually talk with the outside world to actually, figure out your bus routing or whatever. Like all of this is part of a much larger stack that needs to be built up. And this is from a nice paper by, I guess, mostly NVIDIA, I guess, on thinking about basically the how to integrate the QPU not as sort of the prime citizen of everything we're thinking about, but instead as part of this larger workflow. And I think that in the past year or so, this has gained a much greater consciousness of really thinking about how to build out these devices. I think it's really important for us to actually start now because we know what they're going to be, sort of how to interface with them and what they'll be used for, without necessarily having the full power of an error-corrected device. And I guess I guess the quantum brilliance machine is right there. So you guys have practice at doing this already. But I think this is really going to be the future of these devices. Great, which then brings me maybe to the last point on hardware modalities. And I guess if I can survey sort of the main major modalities, one would be neutral atoms, such as our devices at QuEra, trapped ions, such as IonQ or Quantinuum, superconducting devices such as IBM or Google, and then photonic, such as Xanadu or Cyclonum. There's also, of course, sort of what I would call the dark horse technologies, such as topological qubits or quantum dots, or maybe other more exotic devices where we might be able to actually sort of scale out these devices. But in this way, right, we have a wide range of different, substrates that our qubits actually go on. And it might be the case that, in fact, neutral atoms might not be the best for certain tasks, and maybe a superconducting device might be good for very fast things, whereas, neutral atoms might be good for long error-corrected algorithms, or maybe a photonic qubits might be good for X or Y, or, I can go on. But I guess I need to put on my QuEra Computing hat for a second and talk about the neutral atom advantage, I guess, which is, I'm very excited about the future of what we're going to be doing with this platform. And I guess there's a few advantages which I see in the neutral atom platform that I don't really see in any other platform. The first advantage, of course, is this notion of very high fidelity as well as massive scalability. So we have some nice demonstrations both on implicitly Gemini through our Magic State paper, as well as a nice paper from our friends at Harvard on very high fidelity gates, or very high fidelity multi-qubit gates, which gives us, the logical primitive of entanglement, as well as because we basically just use lasers to manipulate the state of our atoms, we can easily, dare I say, scale to thousands or tens of thousands of atoms with very few control lines. So for example, there's, some demonstrations of 10,000 plus traps of on these devices, and with some tricks to scale to many, many more. The second advantage is this notion of mid-circuit reconfiguration, which literally means in the middle of your computation, you're actually moving your atoms around between, say, some storage region and some computation region, and then you move them down into your computation region, and then you're able to do many parallel gates at once, right? So this is, just my animation of what this might look like, of course, not in real time. And this is sort of what this Gemini device is doing today, right? And what this mid-circuit reconfiguration means is actually this gives us a nice notion of both efficient quantum error correction design as well as gives us something called transversal gates, which is a very handy primitive for error correction. We're able to sort of more efficiently suppress errors than you might otherwise for, say, a superconducting qubit. Because you're basically just able to take down, your logical qubit patches, right? Say you got logical qubit 1 over here, you just, say bring that surface code patch down, bring down the next surface code patch, and they're able to do, say 50 or however, I guess this is 5. So this is like 25 parallel gates at the same time. And in this way, it's sort of a machine built for error correction. And in fact, I guess we did this recently in this paper on magic state distillation, which is a important primitive for error correction, where basically you take many noisy qubits, which are sort of have an imperfect state. And I guess magic here is actually, magic is the actual definition. It's sort of the computation, gives us the computational power for quantum computing, because basically without these magic states, you're actually able to efficiently simulate quantum computers on classical devices. So you take these low fidelity magic states, right? And you take, say, 5 of them, and then you distill or refine or whatever, distill them down into one good qubit, right? With a higher fidelity. And at QuEra on Gemini, right, on this machine, we did this for distance 3 and distance 5 color codes, which are a specific type of error correcting code. And you can basically see that basically each of these color codes corresponds to a row of atoms in our atom array. And we're able to efficiently entangle these logical qubits together in order to execute this magic state distillation circuit. And in this way, we're actually able to really think about the strengths and weaknesses of our hardware in order to actually get the best out of this near-term hardware and do these near-term demonstrations. Which really brings me to, I guess, my last slide, which is on, I guess, the secret sauce of how we get the most out of today, tomorrow's and today's near-term computers. And the secret sauce is something, I guess, is this notion of co-design, right? Which is really thinking about what are the algorithms which we're running on, which we want to run? What are the applications that we think might actually be useful to and relevant for, say, commercial or scientific applications? And then what is the hardware we have to run that on, right? And then now it's sort of, I guess it's thinking about how we can use that hardware to the best effect so we can design an algorithm, right, that can run on that hardware and identify applications which are efficiently implemented using that algorithms and efficiently implemented on that hardware. And this way we can actually get the most out of, say, Aquila, right, where here we have 256 analog mode qubits and are still able to do important scientific discovery. or say with Gemini, where we have 200 plus digital mode qubits, and we're able to, again, do interesting small demonstrations, as well as some interesting primitives. And there's a lot you can do with 200 qubits. I'm excited to explore more. And then also the same for future devices, where it actually might go both ways, right? Where maybe I have some idea for an interesting code, and that might also inform some of the capabilities of hardware. So this is really, what we love to do is this notion of co-design, where we work with both algorithms and applications. So I guess maybe with that, this is the call to action slide, I guess, of how you can participate, right? It's really thinking about designing algorithms, right? Of like building things that work on hardware, identifying applications that actually have real world relevance, building pipelines and larger infrastructures, as well as integrating this quantum and classical hardware. I guess last but not least would be a shout out to Pascal and team for working with QuEra and taking the first step in our journey towards utility scale quantum computing. So with that, I'd like to conclude and go for questions. Thank you.
Very much, Jonathan. Okay. So we have a few people here in person, but I would like to check to see if there are any questions online. Are there questions online? If there are a few, maybe you can unmute, say where you are, say your name, say where you're from, and then pose a question. So there are a few. Cool.
So I think some of those questions has been posted.
Okay.
Alexis have some questions from the beginning of the session. I think that the first one was probably answered already. These problems are hard. I guess quantum finds some good optimal, right? Or does it guarantees to find the best optimal one?
Yeah. So this is probably with respect to the quantum optimization.
Yep.
Yeah. So this is a great question. Typically, so a lot of questions are hard to solve, right? There's it's very easy to claim that it takes 10 to the 50 years to solve some optimization problem, but the challenge is actually not in exact solutions, but actually heuristic or approximate solution, right? Because you don't need to get the perfect solution, you just need to get one that works, right? And in fact, this is why I guess quantum optimization is actually really challenging, because heuristic classical algorithms are really good at what they do.
Yeah.
Right. So it's really identifying where do these heuristic classical algorithms fail, so that the heuristic quantum algorithms or heuristic hybrid algorithms can have a chance of actually having some real world utility.
I have one more from Alexis. And then we have someone with the hands up. So I'm going to ask Alexis first. How many physical qubits per logical qubit?
So this depends. I guess for the surface code, right, which is one of the logical prototypes, typically you have like n squared. You have one logical qubit, and you have the logical qubits are defined by the number of physical qubits, the number of logical qubits, and the code distance. And the code distance is basically the number of errors that you can suppress before basically going into, I don't know territory. For the case of the surface code, you have one logical qubit, you have n squared physical qubits, and you have a code distance of n. That might be plus minus 1, right? But then for something like the color codes, right, which are basically these codes over here, you're really focusing in on, can I make a minimal code that can suppress, say, 3 errors? So in this case, this is a D equals 5 color code. So this is one logical qubit in 17 physical qubits that has a code distance of 5. Right. So it definitely depends.
Emily, would you like to ask your question?
Sure, thanks. Can you hear me all right?
Yes.
Yes.
Awesome. So yeah, I'm Emily. I'm from Pawsey. I'm a computational chemist. So I want to sort of zoom in on the computational chemistry part. Has there been any sort of demonstrated exponential speed up over classical algorithms? Classical algorithms are quite good for molecular physics. And so I was interested if there's any qualitative advantage to doing this.
This is a great question. So it's really tricky to claim any sort of exponential advantage, right? Because it's exponential with respect to what, right? And it's also what is the chemical precision you really need, right? And in particular, like as you say, things like DFT and other methods are great for most systems, right? And in fact, it's so we actually have this great collaboration with something called QuEra Bio, or Quantum for Biology, where we've been exploring this exact thing of like, can we identify interesting molecules, and I guess particularly biomolecules, which we might be able to simulate or do something with a quantum computer that we might not be able to with a classical computer. And in fact, actually, the answer is pretty negative, where most of the time it turns out that like for organic chemistry, you don't really need a quantum computer to simulate it. Really, this comes back to my question of what are problems that are so hard we're not really thinking about them? Because for example, when you include metals, right, like which have a very high I guess correlation in them, when you include metals in your molecules, these end up being very hard to simulate classically. Then like maybe it's actually molecules like this, which are actually sort of aggressively quantum, dare I say, that you actually this is where a quantum computer might come into play. But this is not necessarily solving maybe every molecular system or every single condensed matter system, but instead really narrowing in on what the hard problems are.
So it seems like if you were to be doing that, the real advantage would come from kind of long-range correlations. And
yes,
that to me would seem to imply that you need a very long and large quantum circuit, like you'd need big decoherence times and big qubit sizes. That doesn't exactly inspire confidence.
So this is why I said that fault tolerance enables utility, right? Because this is exactly the regime where fault tolerant circuits can begin to do real work. And I think that one of the challenges there is that usually if you just kind of dump some molecule through some compiler to find the ground state or something, then it has some excessive number of gates and depth. But the real challenge is, can we actually co-design our algorithm so it actually fits within, say, 100 logical qubits and some reasonable depth in order to encode these non-trivial problems?
And I would say that I'd kind of second Jonathan's statement that the naive thing is that you probably need an enormous quantum computer, but that there are certainly approaches that you can take. I know we've looked at approaches for organic molecules that have high symmetry and reducing the number of gates that are required, taking sort of novel approaches, not looking at assuming logical qubits, but looking at different approaches where you get quite good estimate of the ground state and excited state energy with a faster convergence than the standard quantum approach. But realistically, you probably don't, definitely for the molecule we did, you don't get an actual advantage. But the idea is that there are frameworks where you can imagine that there would be, given enough metals, enough long range forces, and possibly a much bigger quantum computer, you could gain something where it's just hard, like intractable. Not necessarily truly intractable, but just very hard.
Yeah.
Cool. I might get in touch.
This is definitely in the future of quantum computers, not necessarily the present.
Yeah.
Yeah, I might get in touch later so I'm not hogging up all the Q&A time, but thank you for answering.
Thank you, Emily. We have now a question from Henry. Henry, would you like to unmute yourself and ask the question?
Yes, you can hear me. Yes.
Yes.
I was wondering with regards to the extension of surrounding noise problems, like the surrounding environment, like earthquakes or anything, like, or different oscillations or anything with the and otherwise also like with the measurement of the qubits, like the actual sensors, or what do you actually use to measure the qubit states? Is it, what kind of detector is it, and is there any noise problems associated with that, or
This is great. Yeah, this is great. So the measurement depends on the modality. And I guess I'll say neutral atoms because I know it best. Basically, what you do for there is you're encoding the qubit into the electronic state of the atom. So then basically all of your measurement ends up being with lasers and cameras. So you basically drive with, I think it's an 840 laser. And basically this drives some transition, right, which is conditional on the state of the atom, right? And it drives some condition where basically, you absorb the light at 840, but then you scatter it in all directions. So then this makes the atoms fluoresce. And you have a camera which collects the photons to basically see, do I see an atom there or do I not see an atom there, right? And basically this fluorescence is what causes the presence or absence of an atom, and therefore this is what causes the measurement. It's a bit different in, say, a superconducting system where it's, you have some RF pulse, which then can be read out and amplified. But I guess this is how it's done in neutral atoms.
Just on the noise front, some of the challenges also that Jonathan didn't get a chance to mention is that at least for QuEra, each atom is identical, right? There's no fabrication process for the qubit. It's just a manipulation process. But for other like superconducting systems, it's a manufacturing process to kind of get like a really nice, well-behaved qubit that has the same noise or the same time evolution, decoherence time as every other qubit in the system, which adds, if you will, extra noise because not all qubits are identical. Where in the context of ions and let's say atoms, they have to be identical. You're not choosing different atoms, but in more complex stuff, topological qubits and so on, quantum dots, this idea of using quantum dots, there's, let's say, not a measurement noise error, but there's just variability in the noise, which is not necessarily present in other type of modalities, which can be a real challenge also for looking at error correction, because you don't have a uniform response across all the physical qubits to environmental effects.
Yep. And actually, maybe on the same note of noise, it's a very useful classical computational thing. Basically, try and characterize and understand the noise of quantum systems, right? Because now this is not necessarily just simulating the qubit, but actually simulating the entire atom and all of the electric and magnetic fields around it, and its entire interaction with other atoms in the area, which can get very complicated very quickly, especially for superconducting systems, where, as Pascal says, they're all really talking to each other, and they're all a little bit different. You need to characterize that somehow. You do that through simulation.
Yes.
Follow-up questions, Henry?
No, it's a very insightful talk and everything. So thank you for the talk. It's it's very interesting aspects of quantum computing here discussed today. But yeah, thanks for the presentation. So that's good. No more questions for me. So
I might turn to the physical, like people in there. Any questions for the team of people here? No. So I'll have a bold question. So the magic simulation process is pretty cool. But when do you think you'll get to, because you had your roadmap, right, of 10 logical qubits, 30 logical qubits, but there's still obviously a decoherence time. There's a time in which you can gate operations. So they're not, let's say, true fault tolerant infinite gate number of gates. But when do you think you'll get to a logical qubit that might do 10,000 gates with like, or let's go 100 gates and then let's do 1,000?
This is a great question. It's always a little annoying where we have our own internal roadmap and I know the answer to the question.
Yes.
Can't really say it as out loud.
Yes.
But I guess, we've had a pretty I guess maybe I'll say we have a pretty consistent track record.
Yes.
And like one of the neat things about neutral atoms is basically a lot of the components have been sort of shown already, like these large scale arrays, high fidelity gates. And it's just kind of a recipe book of putting things together. So, I think it's going to be a long way to 100 logical qubits, right? Because like, again, a logical qubit isn't a singular thing. It can take many different forms, right? Exactly what that modality looks like, maybe that's subject to change. Like maybe it's, a lot more HPC centric than we realize, or maybe it's something a little different. But I don't know. I personally have usually have like a 3 to 5 to 10 year sort of horizon for these things, and like that's like 10-year horizon for like really doing very cool things. Your buses are being routed with quantum computers, kind of thing. Like that, like it can be stretched and sliced, and maybe we have 1 qubit or 10 qubits, but yeah.
Okay.
Sorry if I'm vague there, but I think it's a great question, but it's a hard to answer.
So I'll follow up with the last very hard to answer question. Unless, okay.
In a context where there's a lot of discussion about the extreme power requirements of GPUs, quantum computing is sometimes put forward as part of the puzzle in green computing. I wonder how you look at the potential there, or
I think that it's one of the places where we can consider quantum computers as an accelerator or a coprocessor, right? Like in the same way that we might have an FPGA, which is great at like correlation tasks or something, like I guess that you're describing the for radio astronomy tasks, right? Maybe these will also be specialized for specific tasks to do very specific things, which would be very hard to do on a GPU, right? I think the interesting thing about the power of these devices is that, especially for neutral atoms, which work at room temperature, the power scaling is like really not bad. Like this device, like 10 kilowatts, and that's like if you include the lights in the room, right? Like it's very minimal power in comparison to the actual like power use of GPUs. And as we scale to thousands or tens of thousands of qubits, you get the computational power of 10,000 qubits, but you get the electrical power of only, maybe several factors more of laser power, right? So there is still some chance of maybe that 20, kilowatt regime where you have much less computational, much more computational power for much less physical power, I guess. But I guess it comes with the caveat of actually figuring out the algorithm that is relevant for that.
Thank you, Edric. We have Alexis wanting to pose a question. Can you unmute yourself, Alexis?
Yes. Hello, can you hear me?
Yes.
Hello, thank you, John. Yeah, I was wondering what is the architecture of for example, this you are calling this a device, but it looks big. So so this is already sort of a cluster with several nodes and a different an individual QPU in each node, or how is the design? Because
so it looks a little different than a sort of traditional classical cluster, in that it's actually basically a bunch of lasers on an optical table, and all of these lasers are routed down into basically a little vacuum cell, right? And inside the vacuum cell, we have a bunch of microscopes which focus all the laser light down into basically maybe 100 or 200 micron spot, right? Which is like the width of a human hair, right? And then that's where we actually do all of our computations, right? So in this way, we have a room full of lasers, or a table full of lasers, all focused down on 100 micron spot where we actually do our computation, right? Of course, this does mean that we need to have some control boxes for the lasers, right, to actually make them, execute in the correct way, right? But now this is like analog signals, and actually, like, I guess if we look at like these control boxes are basically these guys over here. They basically just generate some analog signals, which then go to the laser controllers.
Okay. And then the computers that you show in the roadmap are still that kind of computers. It looks like more like a prototype type of computer rather than ready to sell.
I guess they're, I don't know. I don't know if prototype is the wrong word, because like I guess this is a device which can be integrated into a larger workflow, right? So this is something where in the heart of this we have this vacuum cell, right? And this is connected to classical control electronics. But now at our next computer at ICE, right? These control electronics will now also be connected to a supercomputing center, right? So then now, in the same way that you might spin up a GPU node, right? You might be able to use Slurm or something to to enqueue some task on your quantum device, right? So like actually on QuEra, this is basically how it works, right? We have the entire queue system, everything's done fully automatically, and basically we have just a bunch of cloud infrastructure to basically execute these without ever really needing to touch the device. Okay, cool.
Yeah, that's a different idea in my this means, but that is much more clear. Thanks.
Are there any follow-up questions or? Okay, so I'll end with another hard one.
Your hard question, okay.
Which is, because you mentioned it as well, right? These different technological modalities have advantages and disadvantages. So realistically, do you think the idea would be that you'd have 6 superconducting QPUs and then 10 neutral atom QPUs in the next quantum computing center? Like, do you expect there to be some real heterogeneity introduced into the QPU ecosystem as well?
Maybe I need to answer that question with the QuEra hat on and the QuEra hat off.
Yeah.
So with the QuEra hat on, I think that actually a lot of the flexibilities of the reconfigurable neutral atom architecture really mean that we are able to do basically everything we might want to do.
Yeah.
Right. That being said, that flexibility also might look something like an FPGA, right? Where you can design your algorithm in one system, and then you make a special purpose chip that does exactly that one thing.
Yeah.
Right. So now, if I take that hat off, it might be that maybe you use your neutral atom system for large scale computation, right? But then now, if you want to do magic state distillation, right, which requires a lot of sampling, right? Maybe this is then a device you do on a superconducting chip, right? But now what this requires is interconnects. Right?
Yes.
We're able to take your quantum information from one chip or modality to another, right? And this is, there's this field is growing pretty nicely, but I think this is the important next step to consider if we really have like a quantum internet or where we have many different devices which are processing at different scales and with different strengths. Say I have some quantum sensor over there which is generating quantum information about some molecule, and then it's sent to the neutral atom QPU for memory, and then it's sent to the trapped ion system to do some computation, then sent back to the neutral atom or whatever ends up happening, right? Probably there's going to be some notion of different modalities for different things. Yes, that's QuEra hat off.
Yeah.
I have one more question from Jawahar Kumar. Sorry if I'm not pronouncing it properly, Jawahar. With the earlier prediction of quantum maturity expected around 2030, initiative toward the post-quantum cryptography has just started in industry sectors. As you have mentioned, 2025 is going to be an exciting year with new scaling expected. What would be your suggestion in handling encryption?
This is so I guess I can probably say that we're not going to be able to safely say we're probably not going to beat RSA in 2025. Right, that's probably not controversial.
Yeah, that's a reasonable thing.
Yeah, very, very reasonable. Like, if someone else has different opinions, then that's but I guess post quantum cryptography, like we have the standards already, right? And now it's just basically a notion of transferring everything over to those new standards, right? And in this sense, basically, we have some window where you have relevant encrypted data, which is encrypted with RSA, which maybe after 10 years becomes not relevant, but you store it for the next 10 years and decrypt it 10 years from now once you get that device. So in this sense, like, making sure you have the post-quantum crypto today so that people don't, store it now and, decrypt it later, that does give at least a little bit of urgency to making sure we have these post-quantum standards.
Yeah, I'm going to follow up that effectively, I think the push is if there is something that you think would be relevant years down the line,
That's right.
Then it probably behooves that organization to consider post-quantum encryption now, because perhaps, it might still be 10 years down the line, but 10 years down the line, if it's still relevant 10 years from now, then it gets decrypted, right? So that is part of the push. I think that's also part of the reason why people are looking at post-quantum encryption, and Apple's kind of uses it as something to do now, because you might as well do it now, even if the computer that can run Shor's algorithm kind of quickly and without any issues is a decade away. You might as well start doing it now, just to get around that. I'd like to thank you again, Jonathan, for a great talk, very insightful and thought-provoking as well. And I'd like to thank the audience for their questions, and wish you a good day.